Hello everyone, my name is Rongrong. I'm a bioinformatics engineer from Sage Bionetworks. Today I'm going to present our ongoing challenge meta-analysis in order to identify the features that maximize engagement in different challenges. First, what's the purpose and why we are doing this work? If you don't know, dream challenges are challenges in general, community competitions that invite public participants to submit their solutions, algorithms to address various not limited to biomedical questions in order to improve reusability of many advanced competition methods. And then from 2012, Dream Challenge has organized and completed more than 45 challenges. While most of the challenge outcomes have been published in well-known peer-reviewed journals, it's time to review the challenge themselves to understand more about how to make challenge successful, what makes challenge effective, and what could be improved. Before going into our global distance results, I would like to show you our first exploration attempt to make a cluster heat map. We use more than 20 different features of challenges, including data types, number of submissions, whether it provide price, etc. And yes, the data we have is mixed type data. So we first transform non-numeric data into one-hot encoding data, and numeric data was log transformed because it's highly skewed, as you can see in figure 2a, along with the minimax normalization. However, as you can see, there are a lot of sparsity in the heat map here in figure 2b, and it's not easy to interpret. That's because we have a lot of category data and missing data, and that's a pain. Therefore, we decided to use Galway distance method, which work well for mixed type data as well as can handle missing data. And the heat map on the right shows the dissimilarity matrix of dream challenges using Galway distance. We can see 3 clusters already, but we will further use PAM to do clustering since it's better fits for mixed type data set. In the figure 3a, we visualize the clusters of all dream challenges using PAM and slew width plot by picking the highest average slew width. We find 2 clear separation based on the challenge year. Old means the challenge launched before 2016, while the young means after 2016. Also in the figure 3b, the box bar indicates the user engagement data was significantly different between the 2 clusters. User engagement data are the data collected from discussion forum, where participants can ask questions and communicate with organizers. Then we realized the discussion forum was not developed or well known until late 2016. That makes sense why there are 2 clear separation clusters. So we also try to use only the challenges belong to the cluster number 2 from figure 3a and recluster into 5 new groups. And the results of new cluster shows better mix of years in 3C, figure 3C, but the challenge with a similar year still trying to group together. And from the box plot result in figure 3D, we still can see the difference in user engagement data, even we only use young challenge after 2016. Therefore, it seems that user engagement data plays key roles in differentiating the challenges. And speaking to the non-numeric variables, we first transform the data into a contingency table. In other words, we count the frequency of non-numeric variables in each cluster and visualize in the heat map by 4A, 4B figures, where we have 6 categories total. And after we have the contingency table, we use feature exact test to check whether the category is associated with clusters, and the significance then was determined by adjusted p-values less than 0.05. As a result, we found the model categorization and types of contributors were key drivers for clusterings on all data, while the model categorization and incentives were significant differentiators among these new 5 clusters. Moreover, if we evaluate the frequency heat map along with the number of submission and registrants, we found that dockerization did not seem to be a big barrier to submission. In contrast, the higher number of submissions associated with the challenge provide model categorization as a submission method, which is interesting. If we're looking at the figure 4B with figure 4D, participants might be more willing to engage when genomic or image data provided. With all being said, we are still continuously curating dream channels for example, we are working to add another layer of sub-channels to account for how the number of sub-channels changing over time for different channels. And in addition, more channels from other platforms will be integrated into our analysis. For example, the figure 4A shows the goal dissimilarity matrix of the 14 precision FDA channels, and we could already see one outstanding cluster, which we will further explore it. Once we are acquiring enough data and comfortable with selected features, we could build predictable models for effective and popular channels. I would also like to bring up our another developing project, Registry of Open Community Channels, which will serve as a web-based central portal to capture standardized challenge metadata hosted on different challenge platforms. So the data in this matters will also be integrated with a Registry of Open Community Challenge platform. That's all for today's preliminary analysis. I would like to acknowledge my team for all excellent work and all the data contributors from Dream Challenge, Precision FDA to Challenge Golf. Thanks so much.